I'm going to begin by giving an introduction to wireless network standards. To talk about the standards, I need to introduce you to the IEEE 802.11 specifications. These are a set of specifications that deal with the data link layer and the physical layer of the OSI reference model. These establish how wireless network communication can occur. The 802.11 standard specifies the use of unlicensed radio frequency bands as the carrier for network traffic. It also specifies that network communication will be half duplex in nature, and that it will be implemented using carrier sense multiple access with collision avoidance, or CSMA-CA. Carrier sense multiple access with collision avoidance technology requires that devices only transmit data when no other data transmission signal is present on the carrier wave. Now, the 802.11 standards have been amended over time to become our common standards that we see today. These standards include the 802.11b wireless standard. It was commercially released in 1997 and operates within the 2.4 GHz Industrial, Scientific, and Medical, or ISM, radio frequency band. Now, within the 2.4 GHz RF band, it uses multiple channels that are 22 MHz wide. There are 11 separate channels, of which only 3 do not overlap. 802.11b has a theoretical throughput of 11 megabits per second, and it is compatible with the 802.11g and N standards. Then there's 802.11a. It was also commercially released in 1997 and operates within the 5 GHz unlicensed National Information Infrastructure, or U-NII, radio frequency band. It offers up to 23 separate channels that offer a bandwidth of 20 MHz each. None of the channels overlap. 802.11a has a theoretical throughput of 54 megabits per second. It is not compatible with any other standard. 802.11g was commercially released in 2003 and operates within the 2.4 GHz radio frequency band, just like 802.11b. It also offers a bandwidth of 20 MHz on 11 separate channels. It has a theoretical throughput of 54 megabits per second, and it's also compatible with 802.11b. It's also compatible with 802.11n and 802.11ac. And that brings us to 802.11n. It was commercially released in 2009 and can operate on both the 2.4 GHz and 5 GHz radio frequency bands at the same time. It uses a 20 MHz wide channel within the 2.4 GHz band and a 40 MHz wide channel within the 5 GHz band. It has a theoretical throughput of 600 megabits per second through the introduction of multiple input and multiple output MIMO technology and beamforming. And it is compatible with .11b, .11g, and .11ac. And that brings us to 802.11ac. It was commercially released in 2013 and operates on the 5 GHz radio frequency band. The available bandwidth varies by administrative settings and can be dynamically changed by the wireless access point based on how much radio frequency interference, or RFI, is present and how many users are on the wireless network. 802.11ac has a theoretical throughput of over 1 gigabit per second through the introduction of multi-user, multiple input and multiple output technology, or MU-MIMO technology, and beamforming. 802.11ac is only compatible with 802.11g and N. So why broadcast a wide signal to a specific device when it's possible to target that device specifically? This is the question that beamforming answered. Once a device makes a connection to an access point, Once a device makes a connection to an access point that is capable of beamforming, the AP will auto-tune its antenna and transmitter to more specifically target the device when communication occurs. This can reduce RFI and increase throughput on the wireless local area network. While 802.11n allowed for beamforming, it was not a standardized option until the implementation of 802.11ac. Since we've covered the standards, let's move on to antenna technology. First up, the basics. Antennas are used to broadcast and receive radio frequency signals, and they fall into two basic categories. There are omnidirectional antennas, which are designed to broadcast and receive signals in all directions. Then there are unidirectional antennas, which are designed to broadcast and receive signals in a specific direction. Antenna placement and type of antenna will have an impact on wireless local area network performance. Both MIMO and MU-MIMO are technologies that allow for more than one spatial stream to be transmitted and received by a single device through the use of multiple antennas. MIMO allows for up to 4 spatial channels, while MU-MIMO allows for up to 8 spatial channels. MU-MIMO also allows for a single signal to be spread across multiple transmitters. This accounts for the multiple user part of the name. Let's conclude with a discussion on wireless access points. The wireless access point is a foundational piece of the wireless local area network. The wireless access point, or WLAPP, can also be known as an access point, or AP, and it creates a point of entry for wireless to enter the more traditional wired networking environment. The AP can also be used to join other types of networks. Wireless access points in most cases use unlicensed radio frequency bands in order to communicate with devices. One or more antennas are used in order to radiate and receive radio frequency signals in a half-duplex manner. Wireless routers are common in the small office, home office environment. They are wireless access points that have routers built into them, reducing the need for networking components. A wireless bridge is an access point that can bridge wired network segments together in certain situations. Access point performance is impacted by the number of wireless devices that are attempting to access the network. This can be mitigated by adding additional access points to the network. Strategically adding WLAPPs to the wireless local area network can allow users to migrate from one wireless signal to the next. This is called roaming. So let's talk about roaming a little bit more. When implementing multiple access points, you might find that you also need to implement wireless controllers. They're commonly found in wireless networks of medium-sized and larger businesses. They're used to control wireless local area networks that have multiple access points that all function as part of a larger wireless network through the use of special protocols that can increase the usability of the wireless local area network. One of those special protocols is Lightweight Access Point Protocol, or LWAPP, which is a Cisco proprietary protocol that is used by Cisco wireless controllers. Dynamic or static VLAN pooling can be established with a wireless controller. This is taking the wireless local area network signal and creating and controlling virtual local area networks to allow more devices to connect to a single access point. Wireless controllers are often used to create a wireless network mesh that seamlessly spans more area than is normally possible with wireless access points. The mobile devices are seamlessly handed off from one access point to another when they reach the edge of a signal. Now I'm going to begin by talking about wireless local area network topologies. And the first topology is the ad hoc topology. It's a very basic wireless local area network that does not require the use of a wireless access point, which can also be called a WLAPP, and it can also be called an access point. The devices negotiate the wireless connection between themselves. An example of this are when laptops connect wirelessly without the use of a wireless access point. Then there's the infrastructure topology. It's a more common type of wireless local area network that uses a WAP or multiple WAPs to create a connection point for wireless devices. Most often, it's used to connect a wireless network to a more traditional wired network, but that wired network is not absolutely required. Then there's the mesh topology. This is a type of infrastructure topology that employs the use of multiple access points to create larger seamless network coverage areas. They're commonly deployed with wireless controllers and wireless access points. Something to remember is that the higher the wireless device density, the more wireless access points that will be required to handle the load. Like any other network device, access points only have a certain amount of capacity. As the workload increases, the amount of throughput will decrease as each device contends for access to that wireless access point. Adding more WAPs and/or adding more access points and wireless controllers can greatly ease the load and increase the efficiency of the network. Now let's move on to wireless LAN concepts and terms. First up is the IBSS, or Independent Basic Service Set. An IBSS is created when an ad hoc network topology is created. The devices use the IBSS in order to control the communication that occurs between the connected devices. Then there's the BSS, or Basic Service Set. When a single wireless access point is in infrastructure mode, it will create a BSS. This means that it can control the flow of communication between every device that connects to the SSIDs under its control. Then there's the ESS, or Extended Service Set. An ESS is created when two or more access points share a common SSID and have overlapping coverage. Through the Extended Service Set, the WAPs will negotiate how to hand off a wireless device between them as it roams the network. So I mentioned the service set identifier just a moment ago, or the SSID. It plays a key role in the wireless local area network environment. All active wireless access points will use a beacon transmission to advertise the networks that they belong to. What they advertise is their SSID, which can also be thought of as their network name. Those beacons are how devices know which networks they can connect to. Even when an access point is set to hide the beacon, the broadcasts are still occurring. So although hiding the SSID broadcast may make it more difficult to join a wireless network, it's not a true security measure because the broadcast is still occurring. Now let's talk about 802.11a-HT and 802.11g-HT. Both of these terms relate to the 802.11n standard. They denote the type of connection, a high throughput connection, and the radio frequency, which will either be the 2.4 gigahertz radio frequency band or it may be a 5 gigahertz connection. Then there's Goodput. Goodput is the actual amount of application data passed through a connection with the overhead removed. It's measured in bytes per second. It is different than throughput. Throughput measures the total amount of data capable of being passed through a connection, so it includes network overhead. Then we have signal strength. It's a measure of the strength of the radio frequency signal that comes from an access point, which can help to determine the amount of area that can be covered by that access point. As a general rule, the closer a device is to the wireless access point, the stronger the signal that is received. This strength of signal can be affected by wireless access point or antenna placement, the type of antenna used, and interference sources that may be present. A wireless site survey with heat mapping tools can help in the setup of a high-quality wireless local area network, or it can help you to pinpoint problem areas within your network. The heat mapping software builds a visual map by measuring the received signal strength indicator, or RSSI, and the signal-to-noise ratio, or SNR, which can be directly correlated to data throughput. Using these tools allows the administrator to find gaps in coverage as well as areas where the coverage extends beyond the desired boundaries, helping to create a more efficient and secure network.